In this lesson, we're going to look at infinite limits, and we'll look at them graphically, and we'll also evaluate them using the properties of limits. But before we even talk about infinite limits, I want to look at the difference between an infinite limit and a limit at infinity. These are two different types of limits that you're going to learn about. And so the best function to display the ideas of infinite limits versus limits at infinity is the basic rational function f of x equals 1 over x. And so if I look at this first limit, infinite limit, that means the actual limit itself is infinite. So the y values are approaching either infinity or negative infinity. And so when we look at the limit as x approaches 0 from the right of 1 over x, it says here that's equal to infinity. So let's look at what that means. As I let x approach 0 from the right, so my x values are getting smaller and smaller, my y values are getting larger and larger, and they are growing to infinity. So you can see there's that vertical asymptote there. As x approaches 0 from the left of 1 over x, the y values are actually approaching negative infinity, and let's look at the graph. So as the x values are getting closer and closer to 0 from the left, the y values are heading towards negative infinity. So they're growing in a negative direction infinitely. Now, infinity is not defined. It's not a finite value. So when the value of a limit is infinite or equals infinity or negative infinity, we actually say that that limit doesn't exist. But since I can describe the behavior, I will write down the symbol for infinity when something grows without bound in a positive direction, and negative infinity when something grows without bound in a negative direction. So that's what's considered an infinite limit, when the y values are growing without bound. Now a limit at infinity is when the x values are getting larger and are growing without bound towards positive infinity or negative infinity. And so when we look at this first limit here, the limit as x approaches infinity of 1 over x, when we look at the picture, we look at the graph, I'm letting x get larger and larger. And at 5 already, y values are pretty small. You can see that you are approaching 0. It makes sense that when a numerator is fixed and a denominator grows without bound, that you're going to get fractions that have lesser and lesser value. 1 over 100, 1 over 1,000th, 1 over 1 millionth. So the limit as x approaches infinity of 1 over x is 0. And we have a horizontal asymptote there. And we'll explore asymptotes in a little bit. The limit as x approaches negative infinity of 1 over x, well, let's let x get smaller and smaller. What happens is our y values are approaching 0. They will approach 0, but they can never hit it. And so the limit of 1 over x as x approaches infinity, and also as x approaches negative infinity, is equal to 0. So in summary, an infinite limit is when your x values are approaching a finite value and your y values are growing without bound. And a limit at infinity is when your x values are approaching negative or positive infinity and your y values are approaching a finite value. So here we have basically what I just said, the definition of an infinite limit. In this lesson we're going to talk about infinite limits, and then in the next lesson we'll talk about limits at infinity. And so here we have the definition of an infinite limit, and right underneath we have the definition of a vertical asymptote. And so when x approaches a constant from the left or from the right, and your y values approach positive or negative infinity, you have a vertical asymptote. Another way of saying that is when the dependent variable, which is your y, or your f of x, increases or decreases without bound, as the independent variable x approaches a finite value, you'll have a vertical asymptote. So we really just have some new notation to use when talking about asymptotes. But finding asymptotes, we can use the same exact methods that you learned in your pre-calculus course or an earlier algebra class. So let's look at example 1. We want to find infinite limits graphically, and so we're going to look at the graph. We already have it graphed of f of x equals x minus 2 over x minus 1 squared times x minus 3. So it says state the vertical asymptotes, and you can use algebra for this part. So you don't have to use the idea of a limit. You know, or should know, that once a rational function is reduced completely, you'll find vertical asymptotes by setting the denominators equal to 0. Doing so results in a vertical asymptote of x equals 1 and a vertical asymptote of x equals 3. So you can see that visually where those asymptotes are. Now we're going to evaluate the following limits. And we can use the graph to evaluate these. And then later we'll talk about how you evaluate infinite limits algebraically if you didn't have a graph in front of you, or if you didn't want to actually draw the graph. So we'll start with the first one in part B, the limit as x approaches 1 from the right of f of x. So here's 1, and as x approaches 1 from the right, the y values are growing without bound. So we say we're going to infinity. So the limit is infinity. Again, not defined, but we're able to describe the behavior. Let's look at the next one. The limit as x approaches 1 from the left of f of x. So as I approach 1 from the left, my y values are growing without bound. We have another infinite limit. Since the left and the right hand limits are the same, again, even though they're not defined, they are both going to infinity, I can state that the limit as x approaches 1 of this function is equal to infinity. Infinity is not defined, it is just describing a behavior. Let's look at the next one. The limit as x approaches 3 from the right. So here's 3. As my x values approach 3 from the right, my y values are going to positive infinity. The limit as x approaches 3 from the left, as my x values approach 3 from the left, my y values are going towards negative infinity. So here I've got my one-sided limits. One is positive infinity and one is negative infinity. That means that the limit as x approaches 3, not only does it not exist, like none of these do, but it can't be described because the one-sided limits are not equal. So here we would say does not exist. I want to summarize again about how you use infinity in your answer. Right. If you can describe the behavior as positive infinity or negative infinity, then you want to write that down. Technically, none of these limits exist because infinity is not defined. But the only time I'm going to write does not exist is when the left and the right hand limits are not equal. All right, let's look at evaluating an infinite limit algebraically. So we won't graph this. So we can graph it when we're done to check our work, but for now we want to try and graph this without using a calculator. And just to remind you that all of the tests in this class are part calculator, part non-calculator. So there's always going to be a time when you're going to have to do something analytically and you won't have that backup to check your work. Alright, so I have the limit as x approaches 0 of 5 plus x over x. When I substitute in, I get 5 over 0. So we know that 5 over 0 is undefined, and we know that just by looking at this algebraically that there's a vertical asymptote at x. You don't need to have had any calculus to know that. But how do I figure this out analytically? When the denominator is equal to 0, one of three things, or one of three answers is going to be possible. One, the limit is going to approach infinity, or the function will approach infinity, so we'll state that the limit is infinity. 2, the limit is negative infinity, or 3, the limit does not exist. So to test this out, we're going to do a little, we'll make a sine table at 0. So what I want to do is I want to find the limit as x approaches 0 from the left of this function. I want to find the limit as x approaches 0 from the right of this function. And if these two limits are both the same, in other words, they both either go to positive infinity or both go to negative infinity, then I can state an answer using positive or negative infinity. If they're different, the answer will be does not exist. Now, to make a sign chart, not only do I need to know where the denominator is equal to 0, I know the denominator equals 0 when x equals 0, but I also need to know when the numerator is equal to 0. The numerator is equal to 0 when x equals negative 5, and so I'm going to mark that off on my sign in my sign chart. What I need to do is pick a number in the interval to the left of 0 and an interval to the right of 0. And I would need to pick the value to the left. I would need to pick one that is between 0 and negative 5. And so I would pick negative 1 for a test value to the left, and in this right interval here I would pick positive 1. I'm choosing values that are just easy to use, and all I care about is the sign. Is when I plug negative 1 in to this function, is the value positive or is it negative? So when I plug in negative 1, I get 5 plus negative 1, which is positive, divided by a negative, so in here is a negative. That means that the limit as x approaches 0 from the left is equal to negative infinity. I'm also going to test this region in here. Remember, if between any two zeros or between any vertical asymptote and a 0, a function is either completely above the x-axis or it's completely below, which is why I only need to test one value in each region to decide whether it's going to be positive infinity or negative. So to test the limit as x approaches 0 from the right, I've chosen 1 as my positive value. When I put positive 1 or substitute positive 1 in the expression, I get a positive value in the numerator. I get 6 divided by 1. Again, we don't care about the value as much as the sign, which is positive. And so this will be positive infinity. Since my one-sided limits do not equal each other, then the limit itself, the two-sided limit, does not exist. The reason why I found out where the numerator was equal to 0 is because I want to make sure that that negative 1 is in, that the test value that I'm choosing is in the right region. Suppose I didn't find out where the numerator was equal to 0 and I didn't have that test point of negative 5, or that boundary of negative 5. And I said, why don't I test negative 6 in this region? Well, if I test negative 6 in this region, I would end up getting a positive value, and that would actually throw my answer off. So we're looking to find out what's happening near 0 on either side of it, but when we pick our test points, we have to be in the correct region. All right, we'll do the next example in the next video.